Hi there, and welcome to Raylene Math. In this video, we will look at word problems, but not just any old word problems. They're specifically word problems about maximum or minimum, biggest or smallest. So these applications of extreme values of functions are called optimization. In this first example, the United States Parcel Service has contracted you to design a cylindrical container that has a volume of 100 cubic inches and a minimum surface area. And it wants to know what are the dimensions of such a cylindrical container. So it'd be worth rephrasing the question into the form of solve for something given something. And in this case, we want to solve for the dimensions of a cylindrical container. So it pays to picture a cylindrical container or a cylinder and know that the dimensions are height and radius. So we want to solve for the radius and the height such that, or given that, the volume is 100 cubic inches and the surface area is a minimum. And so from here we realize that we're looking at a graph, and on that graph we want to have a minimum value. The key is to figure out what goes along the vertical and horizontal axes. The thing that we want to find the minimum of is a point that has both an x-coordinate and a y-coordinate. And here the y value is the minimum value we are looking for, but we are asked to find the dimensions, so the input would be either the radius or the height, depending on how we set up our input, and the output is the surface area. So this is the minimum surface area height right here, and there are lots of other heights on the surface area graph. Okay, so I've set up a few steps, and if we follow these steps, we'll be able to set up almost every optimization word problem. In the first step, we want to define the variables. If we can draw a sketch or label a diagram, we can combine these two steps into one. So here we have our cylinder with the radius and the height labeled. I'm going to use lowercase letters for the input variables and uppercase letters for the output variables. So we're going to let r be the radius, h be the height, capital V for the output be the volume, and the volume depends on the radius and the height, so it's an output or a dependent quantity. And lastly, we are going to let area or surface area be called SA or A. And so from here we have all of our variables. Notice that we didn't use X or Y, and there's a reason for that. So avoid using X or Y. Oops, do not use X or Y, because very often if we were to call the radius X and the height Y, we would have to come up with the volume as a function of the radius and the height, and that would mean that the Y is part of the input and not the volume, which we're used to Y being. So don't introduce X and Y until later on. In fact, you never need to, but if you do want to use it, wait until later on in the process. Okay, so the next step is to write the equations. We know that the volume of a cylinder is given by the area of the base multiplied by the height, and the base is a circle, so its area is pi r squared, and the height is h. Furthermore, we have the surface area dependent on the radius and the height. If we imagine a soup can, we have two circles for the ends, and then the soup label can unravel, and that forms the sides. Now this soup label has a length here, which is the circumference, and the circumference is 2 times the radius. So that's the same circumference here. Sorry, it's 2 pi r times the radius, that is. And then the height of the soup label is the height of the cylinder or the can. Meanwhile, the area of each of the ends of the cylinder are pi r squared. So the surface area is 2 pi r squareds, one for the top and one for the bottom, plus 2 pi r h multiplied by 2 pi r times h for the area of this rectangle. The next step is to eliminate the variables, and we were given that the volume, which is equal to pi r squared times h, is a known 100 cubic centimeters squared. This allows us to either isolate r or h. Now the problem doesn't specify to only solve for r or only solve for h, and so we can eliminate either one of these variables. From the algebra, it's easier to keep the r squared and eliminate the h, or isolate the h. So we can say that h is equal to 100 divided by pi r squared. Then we can substitute that into the second equation, which currently is a formula in terms of both r and h. And so eliminating h gives us a formula for surface area, or a function for surface area, only in terms of r. So this is 2 pi r squared plus 2 pi r multiplied by 100 over pi r squared. We can simplify that and write the surface area as a function of one input is 2 pi r squared plus, reduce the pi's, reduce one of the r's, and we get 200 over r, or 200 times r to the negative 1. From here we can start to see that x is the one input of the radius and y is the one output of surface area, which is a function of only the radius. And so this allows us to see one input along the horizontal axis, and y, which is not the height, which might have been chosen as a variable in the first place, is the output quantity of surface area. So now we can rewrite the equation if we want in terms of the surface area, in terms of x and y, but we don't have to. If we want to, it would look like this. Y equals 2 pi x squared plus 200 times x to the negative 1. I think it's important just to keep the picture, the graph, labeled in mind so that we can see what's the output and what's the input quantity. The next step is about determining the domain restrictions. This allows us to see if the function has, if the graph has any endpoints, because we also need to consider that the absolute maximum or minimum could occur at the endpoints. So we have to think about any restrictions on the radius and the height, which are the two input quantities. We know that the radius is positive, but not equal to 0, otherwise we wouldn't have a container, and furthermore the height is positive. Now we know that the height has been substituted by 100 over pi r squared, and that is to be greater than 0. Now I've set this inequality up using two colors because I want to think graphically to solve that, or simplify it to say that r is greater than or less than something. So I'm going to do this by recognizing that 100 over pi is just some constant, and so that constant is positive over r squared, and that allows me to think of the parent function, which is like 1 over x squared. So if I think of solving graphically, I'm going to compare the red graph, which is y equal to 0, with the blue graph, which is like a vertical positive scaling of 1 over x squared. There's no reflection because the k value is positive. And so that I see that the solution to this inequality is the same as saying r is non-zero. So this says r is contained in the reals, but not equal to 0. Intersecting that with the other condition, that r has to be positive, and we get that the domain is simply r greater than 0. And r, of course, is the same as x. So the domain of our function is x greater than 0. So the next step is actually to find the max or the minimum of the function, and in this case the surface area is to be a minimum, and the surface area is y given by 2 pi x squared plus 200 over x, or times x to the negative 1, where x is greater than 0. And so we can draw this graph by hand, or if it's not possible to draw by hand, we could draw it using technology. So let's use the graphing program and type in the function y equals 2 pi x squared plus 200 over x for x greater than 0. So the curve is outside the region shown, and we can just modify the window. You can just keep changing the values until you see something realistic. If that graph didn't show up by then, we could customize the window a bit further. So I'm actually going to just keep that graph, move it over here a little bit, and trace along until we get the minimum point. And so that minimum point occurs at a certain x comma y ordered pair. Let's just take a screen snapshot of that. And the x coordinate, or the radius, is 2.515 for the minimum surface area or height of this graph of 119.3 square inches. And so we have that function plotted here, and we can see that x is the radius and y is the surface area, and that point, that minimum point, occurs at 2.515 inches for a surface area of 119.27 square inches. And so this allows us to solve, or to state the answer to our question. We were asked to come up with the dimensions of the cylinder. So the minimum surface area, now we weren't asked to calculate the minimum surface area, but if you're unclear, you can do it in a hidden way. The minimum surface area of 119.27 square inches occurs for a radius, which was the x value, of 2.515. Yeah, so 2.515 or 2.52 inches, and a height of, we had 100 over pi r squared, and so we can plug that number into a calculator, and we should use the exact value. It's kind of hard to do. I can just plot it here. 100 over pi times 2.5154, I believe it said. 5152, I don't remember. And that value squared gives us 5.031, or 5.03. And that would be in inches as well. And so we answer the question. Now, if we didn't have technology, we now have a method using calculus to find the maximum or the minimum. And we know that we would be looking for candidates of the extrema first, and the candidates can occur either at the endpoints, which are either left endpoints or right endpoints. But since we found that the domain of the function, the surface area function, is from 0 to infinity, we have no endpoints. And so the only possibilities for a maximum or a minimum occurs at an interior point known as a critical point. A critical point is specifically a point for which y prime equals 0, meaning the original function has a horizontal tangent, or where y prime does not exist. And does not exist means something like 0 over 0 or non-zero over 0. And so we have critical points either at horizontal tangents, I'll just write it underneath, or we have critical points at cusps, corners, or vertical tangents. Now we know a vertical tangent never produces a maximum or a minimum, but we don't know which of these, when we solve y prime does not exist, we might not know if we have a cusp or a corner or a vertical tangent. Furthermore, a cusp is always an extreme point. A corner and a horizontal tangent, they may or may not be a maximum or a minimum. So we would have to test all of these critical points to see if there is a sign change in the derivative, or to see if we have positive concavity or negative concavity at those critical points. And so now we have to work out y prime. If we recall, y was equal to 2 pi x squared plus 200 over x, or 200x to the negative 1. We can get that y prime is equal to 4 pi x minus 200 x to the negative 2. And so it'll be very nice to rewrite y prime with a common denominator, and we do that by multiplying by x squared over x squared for the first term, and we get 4 pi x squared minus 200 all over x cubed, sorry, that should be x cubed in the top and then x squared in the bottom. And so if we want to solve y prime equal to 0, we have to make sure that there are no common factors in the top and the bottom, and there are not. So we simply solve 4 pi x cubed minus 200 equal to 0, which means 4 pi x cubed equals 200, or pi x cubed equals 50, and therefore x cubed is equal to 50 over pi. And thinking graphically about this equation, we have the x cubed graph is a one-to-one function, and we're intersecting that graph with a horizontal line at a height of y equal to 50 over pi. And so if I just draw that in green, we see a red graph intersecting a green graph, and that occurs at only one intersection point. That's because the x cubed function is 1 to 1, which means we can apply the inverse of cubing, namely the cube root function, to solve for the one answer for x. And so x, or the radius, is going to be the cube root of 50 over pi. There's no other solution, but that doesn't mean that we automatically have a maximum or a minimum. And just because we have, even if we do have an extrema, it could be a maximum instead of a minimum. So we need to test to see that we have either the right increase to decrease or decrease to increase change, or the correct concavity associated with the minimum that we want. Solving for the other possible critical points, we see that a 0 in the denominator occurs when x squared is equal to 0, and therefore x is equal to 0. But that's excluded in the domain, and so we have an extraneous root here. There's only the one critical point. So now we need to proceed with either the first or second derivative test on the one and only critical point. Because we don't have any endpoints, and because the second derivative is easy to work out, we could try working out the second derivative to see if we get a positive or negative concavity at that critical point. So y prime was equal to, let's just double check. Let's not use the fraction, but rather the first version, 4 pi x minus 200 x to the negative 2. Let's just write that down. 4 pi x minus 200 x to the negative 2, and therefore y double prime is equal to 4 pi plus 400 x to the exponent negative 3. I'm not going to bother getting a common denominator here because I'm simply going to evaluate the second derivative at the critical point that we found, which is the cube root of 50 over pi. So that's going to give 4 pi plus 400 over some positive number cubed, and that result will be positive. So we had that y prime at the cube root of 50 over pi was equal to 0. It was a horizontal tangent type of critical point. So here is the horizontal tangent, and at that point we are told now that the second derivative is positive, and therefore the concavity is upwards. And so we have just identified a minimum. There is no other possibility or candidate for a minimum, so we've got the absolute minimum. And so we now know that there is going to be a minimum on the surface area graph at the cube root of 50 over pi, comma, the surface area evaluated at the cube root of 50 over pi. Now this is not a very easy number to work with without a calculator, and so to plug this into the surface area formula would not be a very good task. That's why we were just asked to find the radius and the height. And so we know that this is the x-coordinate, or the radius, and this is the surface area coordinate. And so in step 8, in order to answer the question, we would say the minimum surface area, which we were not asked to calculate, occurs for the radius equal to the cube root of 50 over pi and the height of 100 divided by pi times the cube root of 50 over pi, which is 50 over pi to the 1/3, and then we square that radius. So here I can actually simplify this a little bit. I'm going to get 100 over pi times 50 to the 2/3 over pi to the 2/3, and that gives me 100 over pi to the 1/3, 50 to the 2/3. And these are both measured in inches. So we should just confirm numerically to see that those are actually the values that we got by using technology. So if we go to a program, we can evaluate, or just approximate even, the cube root. I'll do it this way. The cube root is raised to the 1/3 of 50 over pi. And if I approximate that, I get 2.5154. And then 100 divided by that value squared. Rather, it's pi times that value squared. And then we're going to square that value for the radius and approximate it. We get 5.0308 as we found for the height before. And if we take these two values and put them into the surface area formula, which is 2 times pi times the radius squared plus 2 times pi times the radius times the height, evaluated such that the radius is this value and the height is this value, we get that the surface area works out to be that minimum value we found of 119.3 approximately square inches. So we have indeed found the correct radius and height to produce a minimum surface area. Well, there you have it. Going through these 8 steps all the time should lead you always to an easy pattern, easy way of getting through these optimization word problems. That's it for now. Stay tuned for more videos on examples of optimization.